Hello and welcome to this Python tutorial. So now we know how to implement two feature extraction techniques. These are PCA and LDA, but these feature extraction techniques work on linear problems, that is when the data is linearly separable. And in this section we're going to see one new feature extraction technique, but this time adapted for nonlinear problems where the data is nonlinearly separable. So this technique is called Kernel PCA. Kernel PCA is a kernelized version of PCA where we map the data to a higher dimension using the kernel trick, and then from there we extract some new principal components, and we're going to see how it manages to deal with nonlinear problems. So we're not going to work on the same problem as we did in the previous sections with the wine dataset, but we're going to work on the same dataset as the one used in part 3 classification, because now we need visuals. We need to clearly see what happens. We need to see how Kernel PCA manages to extract some new independent variables, the principal components, even when the problem is nonlinear, that is, when the data is not linearly separable. And this dataset that we used in part 3, the social network ads dataset, well, remember it was clearly a nonlinear problem because nonlinear classifiers showed much better performance. So let's take this dataset and let's apply Kernel PCA to see how it will handle the nonlinearity. So let's find this dataset into first File Explorer, then our Machine Learning A to Z folder, then Part 9 Dimensionality Reduction, and Section 45 Kernel PCA. So as you can see, we have our dataset, Social Network Add CSV file, the same as in Part 3. Make sure that you have it in the folder, and if that's the case, you're ready to go. And now what we're going to do is take this logistic regression model, because you know this logistic regression model is a linear classifier. Therefore, it will not be appropriate for our problem because our data is not linearly separable. So what we're going to do is take this linear classifier here, but we are going to apply Kernel PCA inside of it to see how Kernel PCA will save the situation. And so you will see that even if we apply a linear model, well, thanks to Kernel PCA that will manage to extract new principal components adapted for this non-linearly separable data, well, you will see that we'll get amazing results. So right now, let's copy the whole model here from the top down to the bottom, copy, and let's paste it in our Kernel PCA file. All right, and now, basically, the only thing that we have to do is to apply Kernel PCA at the right place. But before we do that, I would just like us to visualize again why this linear model is not appropriate for this dataset. So what we're going to do is take everything from here, because this will visualize the training set results by plotting the prediction regions and the prediction boundary. So we're going to take everything from here up to the top to import the dataset, apply the preprocessing phase, fit the logistic regression to the training set, and eventually plot the training set results. So let's do it. Let's visualize this again very quickly, and that will give us motivation to apply Kernel PCA. And here we go, all executed properly. That's the result. Let's zoom on it. All right, here it is. So as a reminder, the points are the real observations, that is, are real customers in the social network, represented by their age and their estimated salary. So that's our real observation points, and our predictions are represented by these regions, the red region here and the green region here. And basically this red region is where our model predicts that the customer will not click on the ad because we have a 0 here. And this green region here is the region where our model predicts that the customers will click on the ad and buy the SUV. And so remember, the problem was that this straight line here is actually the prediction boundary generated by the logistic regression model. But since the logistic regression model is a linear classifier, then it has to be a straight line here separating the data. And therefore, remember, the problem is that it cannot make some kind of a curve here to catch these green users that should be in the green region. Right now they are in the red region, as well as these green users here that are in the red region. And so this clearly represents the fact that our data is not linearly separable, because we can clearly see that this prediction boundary here that plays the role of separator and that is supposed to separate the two classes, well, it cannot separate the two classes properly because, as you can see, these users are not in the right region. And so now what we're going to do is not make a nonlinear classifier like we did in part 3. You know, when we made kernel SVM, naive Bayes, decision trees, or random forests. Well, what we're going to do now instead is apply kernel PCA so that we keep a straight line as the separator, as the prediction boundary of a linear classifier. That is still going to be the prediction boundary of a logistic regression model. But since we're going to apply kernel PCA, well, this will manage to apply some trick, where the trick is actually the kernel trick to map the data into a higher dimension and then apply PCA to extract new components that will be new dimensions that explain the most of variance. But thanks to this kernel trick, well, you'll see that we'll manage to get some new dimensions in which the data will be linearly separable even by a linear classifier like logistic regression. So let's see that right now. I can't wait to show you this. I'm going to close this, and now let's apply kernel PCA at the right location. So you already know what this location is. It's actually not different than before. We need to apply kernel PCA right after the data preprocessing phase and just before fitting our classifier like logistic regression to our training set. So basically, we need to apply kernel PCA right here. So new section here, applying kernel PCA, and here we go. Let's do it. So let's actually be efficient. We're going to take our code because you're going to see that it is very similar. So I'm going to take the 4 lines here, not this 5th line here with the explained variance vector, because here we clearly want 2 components. So let's copy this and let's go back to kernel PCA and let's paste that right here. All right, so first of all, what is the class that we need to import? Is it going to be PCA? Well, no, it's actually going to be kernel PCA. As simple as that. And we are taking this kernel PCA class still from sklearn.decomposition. So first line done. Then second line, we create an object of this kernel PCA class. So let's not call this object PCA, let's call it this time kPCA for kernel PCA. And of course, here what we're going to do is replace this PCA class by kernel PCA. All right, and inside this kernel PCA class, we need to include one more argument than for the classic PCA. We can actually have a look at it by pressing Command I here. And here we go. Kernel PCA, we have the different informations about the different parameters. And as you can see, there is still this first parameter and components. That is, of course, the number of dimensions you want to get. And of course, since now we're dealing with a kernel method for machine learning, well, we have this kernel parameter, exactly like for kernel SVM. And actually, we have the same choice of kernels we can use to apply the kernel trick for PCA. And the one that we're going to use is RBF, the Gaussian kernel, the most commonly used, and that works very well on most datasets. So let's add this argument here, and actually we have other arguments here like gamma coef 0, kernel params, alpha, fit, inverse transform. Well, we have a lot of parameters, but these are not the most important here. You will see that by just adding this kernel parameter, we'll get excellent results. So RBF, that's the Gaussian kernel, and basically our object is now ready. And now all we need to do left is to use the PCA object on xtrain and xtest by applying from this object the fit transform method on xtrain and the transform method on xtest, exactly like we did for PCA. So we just need to replace PCA here, of course, by kPCA, and same for xtest. All right, now it's ready actually. We are ready to apply kernel PCA to our dataset, and therefore what will happen is that our dataset will be mapped to a higher dimension using the kernel trick, so that will already create some new dimensions, forming a new feature space where our data will be linearly separable. And then, since we are in this new feature space where the data is linearly separable, Well, PCA will be applied to reduce the dimensionality by extracting the new principal components. Alright, so now let's apply the same whole code, but this time with this section included where we apply Kernel PCA. So to do this, we need to reset our console because it's better to start from scratch. So let's click on this tool button here, then restart kernel. Are you sure you want to restart a kernel? Yes. And here we go, restarting kernel, ready. Alright, so now we can re-execute the whole code with this section included, and that's what we're gonna do. So we take everything from here, the end of visualizing the training set results section, up to the top, and by executing this, that will do all the steps in the data preprocessing phase, applying kernel PCA to our data set, fitting the logistic regression model to the training set, predicting the test set results, making the confusion matrix, and mostly, that is what we are most excited to see, the visualization of the training set results. So let's do it. It's actually not what you expect. Well, perhaps you can guess what's going to happen, but as I told you, we're not expecting a nonlinear classifier with a curved prediction boundary. We're still expecting a straight line, but you will see that this time the straight line is perfectly going to separate our data set, the two classes in our data set. And that is thanks to these new extracted features. So now let's execute this whole code. Here we go, and that is what we obtain. As I told you, this is actually kind of new. I'm going to zoom on it and let's describe the results. Alright, so these are the results of Kernel PCA combined to a logistic regression model that we apply on a nonlinear separable dataset. So, first of all the different elements of this plot represent the same thing. The red points are the customers that in reality didn't click on the ad to buy the SUV. The green points are the customers that in reality clicked on the ad to buy the SUV. The red region is the region where our model predicts that the customers don't buy the SUV, and the green region is the region where our model predicts that the customers buy the SUV. So that's still the same thing, but now the most important thing that changed and that we need to highlight here is the fact that our two classes, the red class and the green class, are now much better separated by this straight line right here. We have still some green points in the red region and some red points in the green region, but we can sense that we are in a new feature space where the observation points of the two different classes here are now much better separated. And this new feature space that we're in right now is formed by these principal components that were extracted through Kernel PCA. And so actually this is not H here, an estimated salary, this is now PC1 and PC2 as principal components 1 and 2, and these are the dimensions of this new feature space where our data is now well linearly separable, separated by this straight line that is the prediction boundary of the logistic regression classifier. And so we can appreciate the contrast between the simplicity of the obtained results and the complexity of what happened behind the scenes. Because indeed we have this very simple results here with these two classes separated by the straight line, but what happened behind the scenes is that our original data set in our original feature space was mapped to a higher dimension using the kernel trick to avoid too highly compute-intensive computations, and then by mapping our data set in the original feature space to this higher dimension, well, first that created some new dimensions, and mostly that created a new feature space where our data was then linearly separable. But by doing that we had more dimensions than the original number of dimensions, so we still needed to apply the PCA dimensionality reduction technique to end up with a lower number of dimensions. So then PCA was applied to this new feature space where the data was linearly separable, and through PCA some new extracted independent variables were created that are nothing else than the principal components of PCA. And eventually, we obtained this new feature space formed by these two new extracted principal components resulting from PCA, in which now our data is linearly separable and much better separated by a linear classifier. So I hope you enjoy the results. Know that you can obtain the same results even if your original data is 0% linearly separable. Like for example, if you had all the red points here surrounded by a circle of green points, well, even for this original dataset, well, by using Kernel PCA, you will be able to get a straight line separating your red points and your green points. So that's a pretty powerful technique and that I strongly recommend to try whenever PCA doesn't provide good results on your dataset that therefore might be a dataset of a nonlinear problem. Alright, so that's it for Kernel PCA, and that's also the end of this part, dimensionality reduction. I'm leaving you with this before and after Kernel PCA results, and I'll see you in the next part, part 10, model selection and boosting, the last part of this course where we'll cover a very exciting algorithm in machine learning that is called XGBoost. So I look forward to seeing you in this next part, and